Good morning, Year 11. Today, what you're going to be doing in class is you're going to be looking at differentiating E, and you're going to be looking at differentiating ln, or log base E, or what ln stands for is log of the natural number. And last lesson, we looked at E, and we found out that E is this naturally occurring number. It's not tied to geometry like a lot of numbers we know. It's this standalone, and we investigated it using this idea of continually compounding interest. And we came up that E is this number that comes from a rate of change, a continuous growth, if we will. And because E was such a naturally occurring number, and we discovered that its derivative is itself e to the power of x, the derivative of that is e to the power of x, it becomes the natural number to use with calculus. And we know that, well, e to the power of x, that's an example of an exponential function. Well, if e is so special, we know that log base of e undoes e to the power of x, so log base e must be special as well, and we give it a unique name. We give it ln, and when you see ln, that just stands for log of the natural number, log base e. And I want to start off looking at log base e, and let's look at the gradient of its tangent. So let's start to play with its derivative. And up on the screen here, you can see straight away that black curve is the graph of f of x equals ln of x, log base e of x, and it follows the graph of all our other logs. It's got a vertical asymptote at x equals 0. It continues on to infinity on the right-hand side, so as x approaches infinity, we can see that, but we can see that it's increasing but at a decreasing rate. So as x continues on, our gradient, and if I slide our gradient along as it continues on, we can see the value of our gradient is starting to approach 0. It's never going to reach 0, but it's going to start to approach it. It's increasing at that decreasing rate. Like other log functions, it crosses the x-axis at x equals 1. So it behaves like any other log, but it's got a unique feature to it. So let's investigate that. One thing to remember when we're finding the derivative of something is the derivative can only exist where the graph exists. So if we have a look at this ln of x graph, its domain is x must be larger than 0. So our derivative will only exist for x is larger than 0. And if we grab that around, we know that we're going to get close to a vertical asymptote. You can see I got to 0 over here on the left-hand side, c equals 0. I got to 0 and the tangent line disappeared. It didn't exist. The second I get very close, that's a very small number, but I'm just past 0. That purple dotted line is very faint, but it's appeared back up on the screen. So we know that at x equals 0, the derivative doesn't exist because the tangent doesn't exist at 0. And we can see that something very close to 0, our tangent is really close to vertical, and it's increasing at that point. So if we think about sketching our derivative function, the value of our derivative function very close to 0 is very close to positive infinity. And as we get closer, as we start sliding our way back along the curve, we can see the value of our tangent, the gradient of our tangent, its value, is decreasing rate. So that means we've gone from somewhere up close to infinity, and it's coming back down, and it's slowing down. It's approaching 0. It never passes 0. It never turns. So this curve comes down and then starts to level out, and it approaches another asymptote. It approaches the horizontal asymptote. It never reaches a value of 0, but it gets extremely close to it. So we've got this curve that starts at infinity, comes down, and starts to curve and starts to approach 0. And we've seen a graph like that before, and I just want to highlight one particular value for you. At x equals 1, and x equals 1, our derivative, our value of our derivative, the value of the gradient, is also 1. And if I turn on the graph of its derivative, there it is there. That curve that starts up infinity comes down at x equals 1. The value of the curve is 1. If I can get that, there we go. At x equals 1, it's 1. And then it continues to approach. Now we've seen that curve, or part of that curve, somewhere before. If I just hit enter, and if I say y equals 1 over x, look at that. 1 over x lands exactly on top of that derivative curve. But notice 1 over x has these negative values, whereas our derivative doesn't have any negative values, and that's because the graph of ln doesn't exist at negative values, so therefore it has no derivative down there. So in short, what we have here is that the derivative of ln of x matches the curve 1 on x, and that's its derivative.